In September 2015, two machines on opposite sides of the United States heard something impossible. A sound from space. Not radio waves or light, but the actual fabric of reality vibrating. The machines detected a ripple in spacetime itself, a distortion so subtle it changed the distance between their mirrors by less than 1,000th the width of a proton. Yet that impossibly tiny shiver carried a message from over 1 billion light-years away. Two black holes, each about 30 times the mass of our Sun, had just collided and merged. 3 solar masses, the equivalent energy of 3 entire suns, had been converted into pure gravitational waves in a fraction of a second. The peak power released was more than 10 times the combined light output of every star in the observable universe. And we heard it. Not saw it, heard it. When scientists converted the data into sound, it produced a chirp, a rising tone lasting just 0.2 of a second. The final scream of two black holes becoming one. But here's what makes this truly unsettling. That was just the beginning. Since that moment, we've detected hundreds more of these collisions. We've photographed the shadows of supermassive black holes billions of times more massive than our Sun. We've watched stars orbit the invisible monster at our galaxy's center at nearly 3% the speed of light. And with each discovery, black holes have revealed themselves to be even stranger than anyone imagined. Right now, at the center of our Milky Way, just 26,000 light-years from where you're resting, there's a black hole with a mass of 4.3 million suns waiting in the dark. And tonight, you're going to learn what happens if you fall into it. Hello there, and welcome to the Sleepy Science Channel. I'm so glad you found your way here. Perhaps you've had a long day, or maybe you're someone who finds peace in contemplating the universe's deepest mysteries rather than counting sheep. Either way, tonight's journey is for you. Let your breathing slow. Let your body settle into stillness. Because tonight, we're drifting through the story of black holes, objects that seem impossible, yet exist in staggering numbers throughout the cosmos. Places where time itself slows to a crawl, where a minute for you could be years for someone else, where the rules of reality bend until they break. Some of what you hear may surprise you. Some may challenge what you thought you knew. And some will simply drift through your mind like gentle waves, carrying you towards sleep. And just before we begin, if these calm explorations help you unwind, consider liking and subscribing. It helps others find their way here too. Now, let's begin. Here's a paradox. In April 2019, astronomers unveiled the first photograph of something that cannot be photographed. The image showed a supermassive black hole at the center of the galaxy, Messier 87. But black holes emit no light. They are, by definition, invisible. So how did scientists photograph one? The answer lies in what surrounds a black hole. As matter falls toward it, the gas accelerates to tremendous speeds and heats to millions of degrees, creating an accretion disk of superheated plasma that glows brilliantly. The black hole itself remains dark, but against this bright background, it casts a shadow. To photograph this shadow, astronomers had to create a telescope the size of planet Earth. They synchronized 8 radio observatories across the globe, from Hawaii to Spain to Antarctica, and combined their observations using a technique called very long baseline interferometry. The result was a virtual telescope with a resolution sharp enough to see a grain of salt in New York from Los Angeles. The image revealed a ring of glowing gas, 40 billion kilometers across, with the black hole at its center having a mass 6.5 billion times that of our Sun. The ring isn't uniform. One side glows brighter because the gas is moving toward us at nearly the speed of light. It's sucked. light amplified by what physicists call relativistic beaming. In May 2022, the same team released another image, Sagittarius A, the supermassive black hole at the center of our Milky Way. Despite being much closer, this image was actually harder to obtain. The gas around Sagittarius A completes an orbit in mere minutes, while the gas around M87 takes weeks. As one scientist described it, imaging M87 was like photographing a mountain, while imaging Sagittarius A was like photographing a puppy chasing its tail. Both images matched predictions made decades earlier using Einstein's equations. The shadows were exactly the right size and shape. General relativity, it seems, works even at the edge of impossibility. Black holes begin as stars, but not just any stars. Only the most massive stars, those born with at least 8 to 10 times the mass of our sun, can create them. These stellar giants burn through their fuel in mere millions of years, fusing hydrogen into helium, then building heavier and heavier elements in their cores. When a massive star exhausts its nuclear fuel, the balance tips. For its entire life, outward pressure from fusion has held the star against the inward crush of gravity. When that pressure fails, the core collapses catastrophically. In less than a second, a region the size of Earth shrinks to the size of a city. The collapse releases so much energy that the outer layers explode outward in a supernova. But at the center, something stranger happens. If the collapsing core has a mass greater than about 2 to 3 solar masses, a limit called the Tolman-Oppenheimer-Volkoff limit, nothing can stop it. Not even the quantum pressure that holds neutron stars together. The core collapses past every known barrier, becoming a singularity surrounded by an event horizon. A black hole is born. The first stellar black hole ever identified was Cygnus X1, discovered in 1964. Astronomers observed a blue supergiant star orbiting an invisible companion. By measuring the star's motion, they calculated the companion's mass, far too heavy to be anything but a black hole. The discovery was so significant that in 1974, physicists Stephen Hawking and Kip Thorne made a bet. Hawking wagered that Cygnus X1 was not a black hole. Thorne bet it was. In 1990, as evidence mounted, Hawking conceded. He had lost the bet. But science had won something far more valuable: proof that black holes exist. Current estimates suggest the Milky Way contains between 10 million and 1 billion stellar mass black holes. Most drift alone through the galaxy, invisible. But when they have companion stars, they become visible as bright X-ray sources, pulling gas from their partners and heating it to millions of degrees. If stellar black holes are massive, supermassive black holes are almost incomprehensibly so. These giants lurk at the centers of most large galaxies and have masses ranging from hundreds of thousands to billions of times that of the Sun. Sagittarius A, at the heart of our Milky Way, weighs in at about 4.3 million solar masses. M87 is over 1,500 times more massive. Here's what puzzles scientists. We don't know how supermassive black holes formed. They exist even in galaxies that formed less than 1 billion years after the Big Bang, suggesting they grew to enormous sizes remarkably quickly. Based on current models, one possibility is that they began as seed black holes formed from the direct collapse of massive gas clouds in the early universe. Simulations suggest these seeds could have had masses of tens or hundreds of thousands of suns, then grown by consuming gas and merging with other black holes over billions of years. What we do know is that supermassive black holes and galaxies evolve together. Observations reveal a tight correlation. The more massive a galaxy's central bulge, the more massive its black hole. This pattern suggests the two grow in tandem, shaping each other in what astronomers call co-evolution. For decades, astronomers inferred the presence of Sagittarius A by watching stars near the galactic center. One star, called S2, orbits the black hole every 16 years, racing as fast as 7,650 kilometers per second at its closest approach, about 2.5% the speed of light. By tracking S2's motion with extreme precision, researchers determined that it orbits an invisible object with a mass of 4.3 million suns, confined to a region smaller than Mercury's orbit. No known object other than a black hole could pack so much mass into so little space. Black holes don't just warp space, they warp time itself. Imagine two observers, one floating far from a black hole and another hovering just outside its event horizon. Each has an identical clock. To the distant observer, the clock near the black hole ticks more slowly, dramatically so. 1 hour on the distant clock might correspond to only seconds near the horizon. This is gravitational time dilation, predicted by Einstein, and confirmed by countless experiments. In 1976, NASA launched an atomic clock into space and measured its ticking against an identical clock on Earth. The space-bound clock ticked slightly faster, exactly as Einstein predicted. Near a black hole, this effect magnifies to staggering extremes. At the event horizon, time dilation approaches infinity. From the perspective of someone far away, an object falling toward the horizon appears to slow down, freeze, and fade away, its light stretched toward longer wavelengths. The object never quite crosses. It seems eternally suspended at the threshold, dimming into invisibility. But from the perspective of the person falling, they cross the horizon without hesitation. To them, time flows normally. They see nothing special at the boundary. Only later, as they approach the centaur, do they realize they can never turn back. This creates one of physics' strangest paradoxes. From one viewpoint, nothing ever crosses the event horizon. From another, objects cross it all the time. Both perspectives are valid. They're simply different ways of describing the same reality, shaped by the extreme curvature of space-time. And here's a thought that might unsettle you. If you fell toward a black hole while watching the universe outside, time in the distant cosmos would appear to accelerate. As you approach the horizon, the stars would speed up, galaxies would whirl. Based on theoretical calculations, in the final moments before crossing, you might watch eons unfold before your eyes. Though physicists debate the precise details of this effect. If you were to fall feet first toward a black hole, you'd experience something with a whimsical name, but terrifying reality: spaghettification. As you fall, the gravity pulling on your feet would be stronger than the gravity pulling on your head, simply because your feet are closer. This difference creates a tidal force that stretches you lengthwise. Simultaneously, you'd be compressed from the sides. The result? You'd be elongated in one direction and squeezed in the others, stretched into a thin strand like pasta. But here's the twist. When this happens, depends entirely on the black hole's size. For a stellar mass black hole with, say, 10 times the sun's mass, spaghettification begins long before you reach the event horizon. The tidal forces would tear you apart at the molecular level, millions of kilometers from the point of no return. For a supermassive black hole like M87, the situation is completely different. You could cross the event horizon without feeling anything unusual. The tidal forces at the horizon of such a massive black hole are actually quite weak. You might drift across that cosmic boundary unaware, only to be destroyed later as you approach the singularity at the center. This happens because tidal forces depend on how rapidly gravity changes with distance, not on the absolute strength of gravity. Near a small black hole, gravity drops off sharply. Near a supermassive black hole, the change is more gradual. Astronomers have observed this process happening to entire stars. When a star wanders too close to a supermassive black hole, it can be torn apart by tidal forces in what's called a tidal disruption event. The shredded material forms a bright accretion disk, producing a flare visible across billions of light years. These events occur perhaps once per galaxy, every 10,000 to 100,000 years. But when they happen, they're spectacular. In 1974, Stephen Hawking made a discovery that shocked the physics community. Black holes aren't entirely black. They emit radiation. And over unimaginable spans of time, they evaporate completely. The mechanism is subtle, rooted in quantum mechanics. According to quantum field theory, empty space isn't truly empty. Virtual particle-antiparticle pairs constantly flicker into existence and annihilate each other. Near the event horizon, something remarkable can happen. One member of a puzzle virtual pair can fall into the black hole, while the other escapes, becoming real. The escaping particle carries energy away. To conserve energy, the particle that fell in must have negative energy, which reduces the black hole's mass. This process, called Hawking radiation, is incredibly faint. The temperature of a black hole is inversely proportional to its mass. A stellar mass black hole has a temperature of about 1/10 millionth of a degree above absolute zero, far colder than the cosmic microwave background that fills space. Such a black hole would actually absorb more radiation than it emits, slowly growing rather than shrinking. But smaller black holes are hotter. A black hole with the mass of a mountain would glow with the temperature of the sun, and a black hole the mass of the Eiffel Tower would be hotter than a supernova, evaporating in a brilliant burst of gamma rays. For a stellar mass black hole, the evaporation timescale is almost incomprehensible, about 10 to the seeds, power of 67 years. That's a 1 followed by 67 zeros. The current age of the universe is only about 14 billion years. A supermassive black hole would take 10 to the power of 100 years to evaporate. These timescales are so vast that by the time stellar black holes begin to shrink noticeably, all the stars in the universe will have burned out, galaxies will have dispersed, and the cosmos will be cold and nearly empty. But here's the twist. As a black hole evaporates, it gets smaller and hotter. The process accelerates. In its final moments, a black hole shrinks rapidly and releases its remaining mass energy in a catastrophic burst. Hawking radiation also creates a profound puzzle called the information paradox. Quantum mechanics says information cannot be destroyed. But if black holes evaporate completely, emitting only thermal radiation, where does the information about what fell in go? This paradox has sparked decades of debate, with proposed solutions ranging from subtle corrections in Hawking's calculations to radical ideas about how information might be encoded on the event horizon itself. In 2023, researchers showed that gravitational effects alone, without necessarily requiring an event horizon, can produce particle creation similar to Hawking radiation. If this finding holds, it would suggest that not just black holes, but any massive object might emit a form of this radiation given enough time. On September 14, 2015, at 0950:45 UTC, two detectors in the United States simultaneously registered a ripple in space-time itself. The signal lasted just a fifth of a second, sweeping upward in frequency like a chirp. It was the gravitational wave signature of two black holes colliding over 1 billion light-years away. This was GW110914, the first direct detection of gravitational waves. Ripples in the fabric of spacetime predicted by Einstein in 1916, but not detected until a century later. The detection earned its discoverers the 2017 Nobel Prize in physics. The colliding black holes had masses of about 36 and 29 times the sun's mass. When they merged, they created a single black hole of about 62 solar masses. The missing 3 solar masses was radiated away as gravitational waves in a fraction of a second. The peak power was more than 10 times the combined light output of all the stars in the observable universe. Detecting such waves required unprecedented precision. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, consists of two identical L-shaped detectors, each with arms 4 kilometers long. When a gravitational wave passes through, it stretches space in one direction and compresses it in the perpendicular direction by less than 1,000th the width of a proton. LIGO detected that tiny change. Since 2015, LIGO and its partners have detected hundreds of gravitational wave events. Most are black hole mergers, but some come from neutron stars colliding. In November 2023, the network announced its most massive detection yet, a merger producing a final black hole of about 225 solar masses. These detections have revealed black holes with masses that challenge theoretical predictions. Before gravitational wave astronomy, the heaviest known stellar black hole had a mass of about 15 suns. Now, we know black holes can be 100 solar masses or more. Some of these may have formed through hierarchical mergers, black holes that are themselves the products of earlier collisions. Gravitational waves have opened an entirely new way to observe the universe. For billions of years, we studied the cosmos through light. Now we can hear it through the vibrations of spacetime itself. What happens inside a black hole? This is one of physics' most profound unsolved mysteries. Once you cross the event horizon, you're cut off from the outside universe. No signal can escape to tell us what you experienced. According to general relativity, you would continue falling toward the singularity at the center. For a non-rotating black hole, the singularity is predicted to be a point of infinite density. For a rotating black hole, it's a ring. But most physicists believe these predictions break down at such extremes, and that quantum effects would prevent true infinite density from forming. Here's where speculation becomes necessary. What form would the singularity actually take? We don't know. Answering that question requires a theory of quantum gravity, a framework that unifies quantum mechanics and general relativity. Despite decades of effort, we don't have one yet. Another possibility that emerged from theoretical work: the event horizon might not be smooth and empty. Instead, it could be a firewall of high-energy radiation created by quantum effects. If firewalls exist, you wouldn't survive crossing the horizon. You'd be incinerated instantly. This idea contradicts the principle that nothing special happens at the horizon, and physicists continue to debate whether firewalls are real. For rotating black holes, the mathematics suggests even stranger possibilities. These black holes have an inner horizon and a ring singularity instead of a point. In principle, you might pass through the ring into a different region of spacetime. This has inspired countless science fiction stories, though most physicists believe the inner horizon would be unstable. Inside the horizon, time and space trade roles. The singularity isn't a place you can avoid by turning around. It's a moment in your future, as inevitable as tomorrow. Moving toward it isn't a choice, mofos. It's simply what moving forward in time means once you're inside. We may never know what truly lies beyond the event horizon. It's an absolute barrier to information. But that's part of what makes black holes so captivating. They are places where our understanding reaches its limits. Throughout this journey, we've talked about black holes as distant objects. M87 is 55 million light-years away. The black holes whose collisions LIGO detects are typically billions of light-years distant. Even Sagittarius A is 26,000 light-years from Earth. But here's something that might give you pause. The nearest known stellar mass black hole to Earth is just 1,600 light-years away, practically in our cosmic neighborhood. And in 2023, astronomers found evidence of one potentially as close as 1,000 light-years. Current estimates suggest there could be 100 million stellar black holes in the Milky Way. Most are invisible, drifting silently through space. Based on their distribution, dozens likely lie within a few thousand light-years of our solar system. We just haven't detected them yet. Could one be even closer? Based on stellar population models, astronomers estimate the nearest black hole might be just a few hundred light years away, a distance light travels in the span of several human lifetimes. It's out there somewhere, pulling on nearby gas clouds, warping spacetime, completely invisible unless something ventures too close. For decades, astronomers knew about two types of black holes: stellar mass black holes formed from dying stars, and supermassive black holes at galactic centers. But there was a puzzling gap. Where were the intermediate mass black holes, those between about 100 and 100,000 solar masses? Theoretical models suggested they should exist. They could serve as seeds for supermassive black holes. They might form in dense star clusters, but finding them proved maddeningly difficult. Then came a revelation from gravitational waves. In 2020, LIGO and Virgo detected waves from a merger of two black holes with masses of about 85 and 66 solar masses. The resulting black hole had a mass of about 142 solar masses, the first clear detection of an intermediate mass black hole. But this discovery raised as many questions as it answered. How did black holes this massive form? Stellar evolution theory suggested there should be a mass gap where black holes couldn't exist between about 50 and 120 solar masses. Yet here was a black hole smack in the middle of that forbidden zone. One possibility: it formed through earlier mergers. Perhaps smaller black holes collided and merged, and then that product merged with another, building mass hierarchically over time. If true, some of the black holes we detect through gravitational waves might be second or even third generation mergers, cosmic products of a violent evolutionary chain. Black holes emit no light. So how do we find them? One method: watch for X-rays. When a black hole orbits a companion star, it can pull gas from the star's outer layers. This gas spirals inward, forming an accretion disk that heats to millions of degrees and glows in X-rays. Cygnus X1 was discovered this way in 1964, revealing itself as a powerful X-ray source orbiting a blue supergiant star. Another method: watch the motion of nearby stars. At the center of the Milky Way, astronomers have tracked dozens of stars, orbiting Sagittarius A. By carefully measuring their orbits over decades, researchers determined the black hole's mass with remarkable precision. One star, S2, provided particularly strong evidence. Its 16-year orbit brought it close enough to experience detectable relativistic effects predicted by Einstein's theory. Gravitational lensing offers another avenue. When a black hole passes in front of a more distant star, its gravity bends the star's light, creating a characteristic brightening pattern. This technique, called microlensing, has revealed several black hole candidates drifting alone through the galaxy. Then there are tidal disruption events. When a star passes too close to a supermassive black hole, tidal forces tear it apart. The disrupted material forms a bright accretion disk, producing a flare that can last months or years. These events are rare, but telescopes now monitor millions of galaxies, waiting for the telltale signature of a star being devoured. And now, we have gravitational waves, perhaps the most direct method of all. When black holes merge, they don't just emit radiation. They shake space-time itself, sending ripples across the cosmos at the speed of light. These waves carry information about the masses and spins of the merging black holes, allowing us to study objects billions of light years away with remarkable precision. Each method reveals different aspects of black holes. Together, they've transformed these objects from theoretical curiosities into well-studied features of the cosmic landscape. Not all black holes are the same. Some rotate slowly, others spin at nearly the maximum rate allowed by physics. Rotation changes everything. A spinning black hole drags space-time around with it, creating a region called the ergosphere where nothing can remain stationary. Even light itself is forced to rotate with the black hole in this zone. The ergosphere exists outside the event horizon. This means, in principle, you could enter it and escape, though doing so would require tremendous energy. In fact, physicist Roger Penrose proposed a process whereby energy could be extracted from a rotating black hole. If you dropped an object into the ergosphere in just the right way, it could split, with one piece falling into the black hole and the other piece escaping with more energy than the original object had. The black hole would lose some of its rotational energy in the process. This Penrose process has never been observed, but it's theoretically possible. Some astronomers think the powerful jets launched by certain black holes might tap into rotational energy through a similar mechanism involving magnetic fields, essentially mining the black hole's spin for power. The fastest spinning black holes rotate at more than 90% of the theoretical maximum. At this speed, the event horizon is significantly smaller than it would be for a non-rotating black hole of the same mass, and its shape is noticeably oblate, bulging at the equator like a squashed sphere. How can we measure a black hole's spin? By watching how matter behaves near the event horizon. The innermost stable orbit, the closest an object can orbit without spiraling in, depends on the black hole's spin. Faster spin means the innermost orbit is closer to the horizon. By studying the X-ray emissions from accretion disks, astronomers can infer where this innermost orbit lies, revealing the black hole's rotation rate. Here's a problem that's haunted theoretical physicists for decades. If black holes evaporate, what happens to the information about everything that fell in? In quantum mechanics, information is never truly destroyed. If you know the exact state of a system at one moment, you can, in principle, calculate its past and future states perfectly. This property is called unitarity, and it's fundamental to how quantum mechanics works. But Hawking radiation appears to be purely thermal. It seems to carry no information about what fell into the black hole. A black hole that formed from a collapsing star would emit the same radiation as one that formed from matter and antimatter, or from a million copies of Shakespeare's complete works. If the black hole evaporates completely, all that information seems to vanish. This is the black hole information paradox, and it represents a deep conflict between quantum mechanics and general relativity. Stephen Hawking initially believed information was truly lost, suggesting quantum mechanics might need modification. But most physicists found this unsatisfying. Decades of debate followed, with numerous proposed solutions. One idea: information might be encoded in subtle correlations in the Hawking radiation, too faint to notice, but mathematically present. Another: black holes might not evaporate completely, but leave behind tiny remnants that preserve information. A third: information might be encoded holographically on the event horizon itself, challenging our understanding of how three-dimensional space works. In 2004, Hawking conceded he'd been wrong. Information likely is preserved somehow. But exactly how remains one of the deepest questions in theoretical physics. The answer might require a complete theory of quantum gravity, something we don't yet have. The information paradox isn't just an abstract puzzle. It probes the foundations of reality itself, asking how space, time, and information are related at the most fundamental level. Black holes are not eternal. Over timescales almost impossible to comprehend, they evaporate. The current age of the universe is about 14 billion years. A stellar mass black hole would take about 10 to the power of 67 years to evaporate completely. A supermassive black hole with a billion solar masses would take 10 to the power of 100 years. These numbers are so vast, they lose meaning. For context, if you wrote out 10 to the power of 67 years in seconds, the number would have more digits than there are atoms in your body. In the far future, as stars exhaust their nuclear fuel and die, the universe will enter what cosmologists call the degenerate era. New stars will no longer form. The cosmos will be dominated by white dwarfs, neutron stars, and black holes. Galaxies will drift apart, carried by the accelerating expansion of space. Eventually, even galaxies will dissolve, their stars flung into intergalactic space. In the black hole era, which begins around 10 to the power of 40 years from now, black holes will be the dominant objects in a cold, dark universe. They'll slowly evaporate through Hawking radiation, glowing faintly in the emptiness. A stellar mass black hole will linger for 10 to the power of 67 years. Supermassive black holes will persist for 10 to the power of 100 years or more. Eventually, even they will disappear. When they do, the universe will enter the dark era, an epoch where only photons, neutrinos, and perhaps a few elementary particles drift through an ever-expanding void. The temperature of space will approach absolute zero. Time will continue, but nothing will happen. This is the heat death of the universe. Maximum entropy, maximum disorder, perfect equilibrium. The cosmos reaches its final state, silent and still. But this scenario assumes our current understanding is correct. New discoveries could change the picture. Perhaps dark energy will behave differently than expected. Perhaps unknown physics will emerge at extreme timescales. We're extrapolating current laws across timespans billions of trillions of times longer than the universe has currently existed. For now, though, if our physics is right, black holes will be among the last structures to fade from the cosmos. They'll outlive stars, planets, and galaxies by unimaginable margins. In the end, they'll evaporate into nothingness, leaving behind only the echo of Hawking radiation dispersing into infinite darkness. Before we drift toward sleep, here are a few final revelations about black holes that challenge everything we thought we knew. First, black holes aren't actually holes. The name is misleading. They're more like the densest objects possible, points of matter so compressed that they create regions from which nothing can escape. They don't suck things in like cosmic vacuum cleaners. They simply have gravity, just like any mass. A black hole with the sun's mass would have exactly the same gravitational pull as the sun from the same distance. If the sun magically became a black hole right now, Earth's orbit wouldn't change. Second, you can't see a black hole from close up. Even if you were hovering just outside the event horizon, you wouldn't see a black sphere. You'd see a completely distorted view of the universe, with space warped so severely that light from behind you would bend around the black hole, creating a strange kaleidoscope of images. You'd see the entire sky compressed into a circle behind you, while the black hole would appear as an absence in front. Not a thing, but an emptiness where stars should be. Third, the event horizon has no physical properties. It's not made of anything. It's not a surface. It's a mathematical boundary, a point of no return, defined purely by geometry. If you're falling toward a supermassive black hole and you cross the horizon, you feel nothing. No barrier, no membrane, no sensation. You simply continue falling, unaware that you've just passed the point where escape becomes impossible. Fourth, inside the event horizon, down points toward the future, not toward the center. Once you're inside, moving away from the singularity would be like moving backward in time, geometrically impossible. The singularity isn't a place in space you're falling toward. It's a moment in time you're falling into. And finally, if you could somehow survive inside a rotating black hole and navigate its complex internal geometry, some solutions to Einstein's equations suggest you might emerge into another universe or another region of spacetime entirely. The math allows for this possibility. Whether it's physically real is another question entirely. Most physicists suspect these wormholes would be unstable, collapsing before anything could traverse them. But the equations leave the door open. mathematically at least, to possibilities stranger than any science fiction. Here's a thought that might shift your perspective entirely. Some cosmologists have proposed that our entire universe might exist inside a black hole. The idea emerges from equations in general relativity. When you write out the math describing the interior of a black hole, it bears some resemblance to the math describing an expanding universe. This has led some physicists to wonder whether they might be the same thing viewed from different perspectives. If our universe is inside a black hole, what we call the Big Bang might be the view from inside of a collapsing star in some ways. Another universe. The expansion of our space might be the continued collapse of that star's interior, and the black holes we observe might each contain universes of their own. There's no observational evidence for this idea. It's purely speculative, but it's based on real mathematics, and it raises profound questions. If black holes give birth to new universes, then the multiverse might not be some abstract theoretical construct, but a natural consequence of stellar death. Every sufficiently massive star that collapses would create not just a black hole, but an entire cosmos. This idea connects to another mystery. Why do the physical constants of our universe seem finely tuned for life? If universes form inside black holes and inherit slightly modified versions of their parent universe's physics, then natural selection might operate at cosmic scales. Universes that produce many black holes would have many offspring universes. Over time, the multiverse would evolve toward physical laws that maximize black hole production. It's a beautiful idea. It's also deeply speculative, perhaps impossible to test, but it reminds us that black holes sit at the intersection of our deepest questions about reality. They're not just astronomical objects. They're windows into the nature of space, time, and existence itself. And now, as this journey draws to a close, let the weight of what you've learned settle gently around you. Black holes, objects that seemed impossible, yet exist in staggering numbers. Places where time bends, where gravity tears reality apart, where the universe reveals its deepest nature. We've heard the sound of spacetime itself ringing when black holes collide billions of light years away. We've seen how scientists photographed the invisible, creating telescopes the size of Earth to capture shadows cast by objects from which no light escapes. We've learned that time flows differently near these cosmic abysses, that black holes eventually evaporate over timescales beyond comprehension, and that they may be closer than we ever imagined, perhaps even containing universes of their own. Black holes are not just objects. They're laboratories for testing the universe's fundamental laws. They challenge our intuitions, push our theories to breaking points, and remind us that reality is stranger than we dream. Tonight, as you rest, remember, the universe is vast, ancient, and full of wonders we're only beginning to understand. And somewhere in the darkness, hidden from view but undeniably real, black holes continue their silent dance through space-time. The nearest one might be just hundreds of light years away, warping space around it. At our galaxy's center, Sagittarius A spins in the dark, pulling stars into impossible orbits. And throughout the cosmos, black holes merge, evaporate, and perhaps give birth to universes we'll never see. If you found these explorations thought-provoking or soothing, consider subscribing to Sleepy Science. It helps others find their way here too. Sleep well, dream gently, and know that even in sleep, you're part of this extraordinary cosmos, a universe that may itself be falling toward a singularity we'll never escape, spinning slowly in the dark.